And welcome back to Calculus 2. Today we're going to talk about more applications of first-order linear equations. We're going to talk about orthogonal trajectories, and we're going to talk about mixture problems. First, orthogonal trajectories. So, for example, suppose we looked at an equation, x squared plus y squared equals, well, let's make it 4, right? Well, if you look at that, this is a circle of radius 4 centered at the origin. Awfully drawn, doesn't really matter. So, orthogonal trajectories is a family of curves that wherever they intersect this curve, they meet at right angles. So, for example, every line that goes through the origin is an orthogonal trajectory. So how might you show that? Well, it's actually not that hard. If at their intersection points they're perpendicular, that means their tangent lines are perpendicular too. So, if we look at their derivatives, so I take derivative of both sides of this, take derivative in terms of x, we get 2x plus 2y dy dx equals 0. Move the 2x over, divide by 2y, dy dx equals negative x over y. Now that's the derivative of the circle. That gives the slope of the tangent line at any point. Well, if the tangent line of the line I want is perpendicular to this, well then the slope is a perpendicular slope. And you may or may not remember from college algebra, but if two slopes are perpendicular, they are negative reciprocals of each other. So that means the derivative of the line we want, dy dx, is negative y over x. And if we solve this differential equation, separate variables, 1 over y equals dy equals 1 over x dx, we will get natural log absolute value of y equal natural log absolute value of x plus c, which means y equals e to the c times x, where this could be positive or negative, really. So that means y equals, we will call it ax. So that is the formula of every line that goes through the origin. So yeah, the orthogonal trajectory of the set of circles centered at the origin is just the set of lines going through the origin. So yeah, this is how we find it. We find the derivative, we take the negative reciprocal. Ooh, I screwed that up. Should be the negative reciprocal. I got it right down here, but I forgot the negative from here to here and it came out right. But yes, it should be plus there. So yeah, just take the negative reciprocal of the derivative, then solve that differential equation to get the formula back for the actual correct function. Let's look at an example from the book. And once again, these are problems from Stewart's calculus book, not from Thomas's. But they're very similar to the ones we have in our textbook. There just aren't that many of them, so I didn't want to use them up in case you guys wanted to practice them. So let's see here. Y squared equal kx cubed. So let's see here. If I take derivative of both sides, I would get 2y dy dx equals 3kx squared. So then dy dx is 3k over 2y x squared over 2y. So that's the derivative of our family of curves. And I'm actually going to do something else here because I would like to actually only have a single constant. So I'm going to say k is y squared over x cubed. So that is 3k times y squared over x cubed times x squared over 2y. So that's going to be 3 y over x. No, over 2x, my bad. Alright, now the dy dx for orthogonal curves will then be negative 2x over 3y. Separate variables, 3y, or I just multiply off the y dy equal negative 2/3 x. Integrate both sides. 1/2 y squared equals negative 1/3 x squared plus c. Multiply off the 2 and square root both sides. Y is plus or minus the square root of negative 2/3 x squared plus, I'll call it c1 because 2 times the original constant. Alright, so let's bring up our calculator. It wants us to plot several members of each family on the same screen. So let's see here. We've got y equals, well, let's see, it'd be the square root of, let's just call it 1 for now. Square root of x cubed negative, the same thing. And let's do it with c equal 1. So the square root of negative 2/3 x squared. Let's go ahead and say plus 3. That's 4 for now. Let's see what that looks like. And I'm going to do something else as well. I'm going to go to z squared, which will make my horizontal and vertical units the same. And you can see there, if I zoom in a little bit, we've basically got ellipses, and I don't know, you might call those hyperbolas, but they meet in right angles. Let's do another one. So let's try problem 32. I already screwed this up once, and I'm starting over, so hopefully this attempt will go better. So let's go ahead and start off by solving for k, because we'll need that later. Let's see, y times 1 plus kx equals x. Divide the y. 1 plus kx equal x over y. Subtract the 1 over. Kx equal x over y minus 1, which is x over y, x minus y over y. So x is x minus y over xy. That is to say, k is x minus y over xy. Finding the derivative is fairly easy. We've already got solved for y, so dy dx is got a division, so I guess I will treat it as such. Let's see, bottom is 1 plus kx times the derivative of the top is 1 minus the top x times 0 to the bottom. That is k over the bottom, 1 plus kx squared. Multiply that out, kx minus kx, yeah, you just get 1 over 1 plus kx squared. Then we plug in k. 1 over 1 plus k times x minus y over x, y times x squared. I'm going to factor out the 1 over y on the bottom there. So that's 1 over y times y. That x will reduce that away. Factor out the 1 over y. Got to divide y out of the 1. Got to divide 1 over y out of the 1, which is multiplied by y. So y plus, and then k. Well, that is the k. There we go. Y plus x minus y squared. So these go away, and we just have 1 over x over y squared, which is just y squared over x squared. That is so much nicer than what I got last time. Okay, so that's the derivative. The derivative of the orthogonal trajectories then is dy dx equals negative x squared over y squared. Separate variables, y squared dy equal negative x squared dx. So 1/3 y cubed equals negative 1/3 x cubed plus a constant. Multiply off the 3, cube root, y equal the cube root of negative x cubed plus a different constant. There we go. Because this was an odd power, we aren't getting plus or minuses. So let's take a look here. Let's see. X divided by 1 plus, let's say 2x. Let's say x divided by 1 plus 10x. Then here, let's do 10 minus x cubed. Then the cube root, so to the 1/3. And then we'll do I did 2 up above, so I'll do 2 here. 2 minus, I don't think these will necessarily be the corresponding ones, but 2 minus x cubed to the 1/3. Oh, I'm going to need to change my graphs here. You can kind of see the nice bit of perpendicular even at this angle, though. Yeah, that's looking nice. See, whenever they meet, it's at right angles. So there we go. All right, so the answer, the orthogonal trajectories, is this baby. All right, let's talk about mixture problems. So this is problem 34 from section 9.5 in Stewart's Calculus, page 621. Let's read it and then talk about it. So a tank with a capacity of 400 liters is full of a mixture of water and chlorine with a concentration of 0.05 grams of chlorine per liter. In order to reduce the concentration of chlorine, fresh water is pumped into the tank at a rate of 4 liters per second. The mixture is kept stirred and is pumped out at a rate of 10 liters per second. Find the amount of chlorine in the tank as a function of time. Well, the thing is, right now we don't know the amount of chlorine in the tank, but we can talk about the rate of change of the amount of chlorine in the tank. So what we're going to do is we're going to set up a differential equation for the rate of change of chlorine. And these are always very simple equations in setup. It's just rate in minus rate out. Because that's what we're doing. We're pumping stuff in, we're pumping stuff out. So let's see. We're pumping fresh water into the tank at a rate of 4 liters per second. But the thing is, that has no chlorine in it. So, we're not getting any chlorine in, so our rate in is 0. But then pumped out, well, let's see here. Pumped out at a rate of 10 liters per second, but that's not all chlorine, that's the mixture. So you have to think about how much of that is chlorine. Well, that is the percentage concentration, which is the total chlorine over the total water. Times outflow rate. So, minus the total C, well, we just call that C. Total water, well, we had 400 liters. We're getting liquid in at 4 liters per second. We're losing it at 10, so minus 6 T, where T is the number of seconds. Alright, times the outflow rate, well, that's then times 10. So that's the rate of change of the chlorine, dC dt. And I think this would just be separable. So if it's just separable, we can divide by the C. dC over C is negative 10 over 400 minus 6t dt, which I suppose you can reduce that as we work. Can divide a 2 out of everything. That's probably it. Negative 5 over 200 minus 3t dt. Integrate both sides, you get natural log of c in absolute value equals, I'll let u be the denominator there, 200 minus 3t du is negative 3 dt. Divide out the negative, you get 5 over 3 integral of 1 over u du, which will get you 5 over 3 natural log absolute value of 400 minus 6t, or 200 minus 3t. And then put that in the exponent. C, oh, plus C, forgot the plus C. C equal, let's give that an A. C equals e to the A times 200 minus 3t to the 5/3. I can really ignore the plus or minus, since you do have to have a positive amount of chlorine. You're not going to have a negative amount. So it's just this constant times that. So we'll call that B. Thing is, we can find that because we know the initial concentration. Alright, at time 0, C of 0, we had 0.05 times 400, which I believe is 8. So 8 equals B times 200 minus 0 to the 5/3. So B equals 8 over 200 to the 5/3. And our formula for the amount of chlorine in the tank, C of T, equal 8 over 200 to the 5/3 times 200 minus 3T to the 5/3. There we go. So, like after 12 minutes, you can just plug in 12 and you get an answer. I think that'll finish us off for this section. Next time, we'll come and look at phase line analysis. And then I think we'll actually be done with this discussion of differential equations. A lot of times I take it further into the 2D plane and talk about phase planes, but I really don't think we have enough time this semester, what with everything going on in the nation. So, have one more section, and we'll call it a chapter. See you then.